Friends, very good morning everyone. We have dealt with aromatic hydrocarbons. We have seen the benzene, a typical archetypical example for aromatic hydrocarbons. Today, we are going for the extension of this aromatic hydrocarbons benzene, that is polynuclear aromatic hydrocarbons. By the way, what are these polynuclear means? These are also hydrocarbons like that of benzene. However, it has fused system. It has more than one or more aromatic rings which are fused together. These are as to become polynucleus. That's why these are called as polynuclear hydrocarbons. This has one or more aromatic rings in which the side of the one of the benzene ring or the aromatic ring will be shared with the other aromatic ring. As we know, like that of benzene, they are lipophilic in nature and also non-polar. As they are non-polar and lipophilic, definitely they are not soluble in water. They are generally solids. Its color ranges from colorless to white to pale yellow to pale green and whatnot. The natural source of polynuclear aromatic hydrocarbons are the forest fires and volcanic eruptions. However, we isolate polynuclear aromatic hydrocarbons from fossil fuels such as coal and petroleum, the major source for this polynuclear aromatic hydrocarbon. The polynuclear aromatic hydrocarbons can be classified based on the structure as benzenide polynuclear aromatic hydrocarbons and non-benzenide type of polynuclear aromatic hydrocarbons. Benzenide, as the name indicates, they consist of benzene ring system. Whereas non-benzenide do not consist of benzene ring system, but they are having the ring system which are aromatic in nature, like we have seen over here. Here it is a 7-member ring with a conjugated bond system and a 5-member ring with a conjugated bond system. There's a totally aromatic and they do not have benzene ring. That's why they are classified as non-benzenoid aromatic hydrocarbons. The benzenide polynuclear aromatic hydrocarbons can be classified into isolated and fused types. The isolated system are one which has benzene ring system and they are joined at only one point. One of the hydrogen in the phenyl is substituted with phenyl group. The biphenyls is the archetypical example for isolated benzene ring system. In this fused ring system, they can be classified based on their how they are fused. If they are linearly fused, they come under the class of linear fused polynuclear aromatic carbons, and if they are angularly fused, they come under the category of angularly fused polynuclear aromatic hydrocarbons. A simple example for linear polynuclear aromatic hydrocarbons is naphthalene. It has two benzene ring system in which it shares one side with the other. In angular polynuclear aromatic hydrocarbons, they are not linearly fused. One benzene ring is fused at a different angle. The examples are the naphthalene and phenanthrene respectively. The subject of discussion for today's class is the naphthalene. Naphthalene has a molecular formula of C10H8. It has two benzene ring system and they are fused at ortho position. They are numbered like this. The outer ring is numbered as 1, 2, 3, and 4. The fused part is not numbered, and this is given as 5, 6, 7, and 8. They are isolated from coal tar. 6 to 10% of the total portion of coal tar is naphthalene. It was first noticed as a condensate in the condenser when this naphtha fraction of coal tar was distilled. What is this naphtha fraction? Naphtha fraction is nothing but the middle oil fraction. The middle oil fraction is one fraction of the coal tar which has a boiling range of 160 to 230 degrees centigrade. This middle oil fraction, upon cooling, we get naphthalene as crystals. These crude crystals are separated by centrifugation. It is washed with concentrated sulfuric acid to remove the phenolic impurities. Then it is sublimed to give the pure product. Naphthalene is a sublimable product, and that's why it's more easy to purify this type of compounds. Naphthalene has the following properties. They appear as shining crystals and which are white in color, having a melting point of 80 degrees centigrade and a very strong typical odor. They are volatile and they sublimes upon warming. They are insoluble in water but soluble in many of the organic solvents like ether and benzene. Chemically, they are having structural similarity with benzene. That's why it is also aromatic like that of benzene. As benzene, it can undergo electrophilic substitution. However, the aromaticity of naphthalene is comparably less when compared to that of benzene. Hence, they can have the double bond character in more percentage. Thus, along with electrophilic substitution, it can also undergo addition reactions too. That is the beauty of this naphthalene. The resonance structures of the naphthalene can be written as follows. The benzene ring system, the pi electrons can move from one place to the adjacent place and it can give rise to its conjugated system. Then in this benzene ring system, this is having the double bond and this can also have resonance stabilization and it can give rise to another ring system. It has three stable canonical forms. Let us look into the preparation of naphthalene. Though naphthalene is available naturally and it is isolated from coal tar easily, but however, the coal tar, the fossil fuel, is extincted. As it gets extincted, we have to go for alternatives. As we know, chemists are crazy. Crazy chemists like crazy kernel. They have the interest to explore the synthetic route for each and every molecule present in this universe. Naphthalene was prepared by this method. They took naphthalene and they have broken this over here between the C4 and for A position. If I break the bond over here, I can get a molecule 4-phenyl butene. If I break the bond over here and I reduce the bond at this position at 1 and 2, I'll get 4-phenyl butene. 4-phenyl butene can act as a starting material for the synthesis of naphthalene. Here, this type of splitting of the molecule to give rise to a starting material from which we can synthesize this naphthalene. Splitting of the molecule to get the starting material is called as retrosynthesis approach. As the name indicates, retro means reverse. Retrosynthesis means reverse of synthesis. We take the product, split the molecule such that we get the starting material. That starting material, what we get, we treat with another reagent such that we get our product. This is the strategy which is followed for the preparation of naphthalene. 4-phenylbutene was taken. If I attach the bond between this carbon and this carbon, then I get naphthalene. To do that, the chemists have treated 4-phenylbutene and in the presence of calcium oxide and heat it strongly. And it got cyclized and dehydrogenation has occurred. Dehydrogenation followed by cyclization and gives rise to naphthalene. This is the simplest method of preparation of naphthalene. And we get hydrogen eliminated. Another person, instead of copying this method, he has looked into the molecule construction in a different way. Instead of splitting over here, he has split the molecule like this. If I split the molecule like this, if I remove this part is benzene. That's why I can take benzene as one of the starting material. Benzene, if I want to take, and this part is the 4-carbon donor. The 4-carbon donor, I will take 1, 2, 3, 4. 1, 2, 3, 4. Butadiene. 1, 3 butadiene as one of the starting materials. And this part, butadiene, I want to react with benzene. Butadiene and benzene both are electron rich. As they are both electron rich, they repel each other. Instead, to make butadiene to react with benzene, I have to create the positivity over the here. Instead of taking this benzene, they took benzoquinone. This can act as a diene and benzoquinone can act as a dienophile. Diene and dienophile can react together to form an adduct. That is called as Diels-Alder adduct. This reaction was given by Diels-Alder. That's why it is named after them as Diels-Alder reaction. This Diels-Alder reaction is a type of electrocyclic addition reaction in which the electrons move cyclically without forming any reaction intermediates like carbocation, carbanions, carbenes, nitrines, free radicals, and so on and so forth. The pi electrons in the benzoquinone can move towards this carbon and it has to maintain its valency. That's the pi electrons over here will move to the next carbon and it has to maintain the valency. That's the pi electrons over here. It moves towards this position and the electrons are moving cyclically. That's why they are called as electrocyclic reactions. And addition is taking place. That's why it is come under the category of electrocyclic addition reaction. And I got the naphthoquinone type of structure. The carbonyl I have to reduce. How to reduce the carbonyl group? I can use a reducing agent like zinc, amalgam and HCl. The carbonyl group gets reduced and I have to introduce double bond and get aromaticity to the molecule by carrying out dehydrogenation in the presence of selenium. I'll get naphthalene. The same naphthalene was obtained from 4-phenylbutene and also obtained from benzoquinone. The same molecule with two different approaches. Yes, the problem will be same, but the approach to solve by different people will be different. How we approach make us different. Another person, instead of looking in this angle, he took the same splitting of the molecule like this. He took benzoquinone here. Instead of that, they took benzene. As this part is benzene, benzene he took and he treated with a 4 carbon donor. 1, 2, 3, 4. 4 carbons are there. Here 1, 2, 3, 4. 4 carbons are there. This is succinic anhydride. Benzene has to react with succinic anhydride. Benzene is electron rich, then the carbonyl carbons are positive center. That's why these two can react. That's why they took 4 carbon donor as succinic anhydride and benzene and they reacted together. In the presence, it acts as an electrophile. In the presence of this electrophile, pi electrons moves to one position and create an electron rich carbon ion, and this attacks on the carbonyl carbon which is a positive center, and the bonding occurs and it has to maintain its tetravalency, and the bond between the carbon and oxygen breaks. It becomes O minus, O minus combines with H plus, and the ring opening takes place to give rise to corresponding 3 benzoyl. At 3 position there is benzoyl group, and this is 1, 2, 3 propanoic acid. 3 benzoyl propanoic acid we got. This 3 benzoyl propanoic acid we can take and we can reduce this carbonyl group. We can use a reducing agent like zinc amalgam and HCl, and the carbonyl group gets reduced to give rise to corresponding 4-phenyl butanoic acid. 4-phenyl butanoic acid which is formed, we can take and heat it in the presence of concentrated sulfuric acid, and it undergo dehydrocyclization. When I heat it in the presence of concentrated sulfuric acid, the pi electrons moves towards one carbon, creating a carbon ion center, and here is the positive center because it is attached to an electron deficient oxygen. This is the positive center and this is the negative center. Unlike poles attract each other. This attack on the carbonyl carbon and OH gets kicked off. Concentrated sulfuric acid is a dehydrating agent. It can donate H plus and OH minus. It combines and it loses as water molecule. In the process, it undergoes cyclization. That's why it is called as dehydrocyclization to give rise to a tetralone. This tetralone which is formed, if I reduce this carbonyl group and aromatize it, I'll get naphthalene. I'll take tetralone, reduce it with using zinc and amalgam, I'll get corresponding tetraline, which upon reduction with selenium, it undergoes dehydration, it gives rise to corresponding naphthalene. The two strategies have been used to prepare naphthalene. One is breaking at the position, another is breaking at the ortho position. These are the two strategies by which we can synthesize naphthalene. In the next class, we can deal with other reactions of naphthalene. Till then, have a nice day. Thank you.